This conference will now be recorded.
Let us discuss some very important aspects of the gas separation by using the membrane uh, separational processes. Uh, as we have discussed in the last class, so the certain membranes will allow the gas to permeate through it, and therefore it is the barrier between two phases. So one phase is the feed phase and another phase is no, the permeate phase other side, and there will be concentration difference. In case of the gas, you can find the partial pressure difference uh, in both the phases, both sides of the membrane, and also within the membrane. So you can cite many examples for the gaseous permeation like sulfur gases can permeate through the neoprene rubber, or hydrogen can also be permeate through certain, mostly this is a very useful technique and widely used in purification of the fuel-based gases, where the purity can be enhanced by using this particular technique. Okay, so this I already explained that there will be in the feed phase also you find the one concentration profile, and within the membrane also you can find one concentration profile, and this side also you will find this is a permeate phase. You find the concentration profile in terms of the partial pressure differences, and finally this is the overall equation by which you can find out the rate. So rate is three resistance offered by the one film which is there in the feed phase, and resistance offered by the another film which is there in the membrane, and then we have another resistance to the mass transfer which is offered by the a film which is there in the uh, permeate phase. So the Na will be the total flux which you can able to calculate by using this one, where this is the permeability. So permeability is the product of diffusivity of the component through the solid as well as its solubility. S is the solubility, so which you can define by using this one. And also it will take care the relation between these two. The concentration in the membrane at feed side, and also the partial pressure which is at the interface in the feed side. This two will be related by the Henry's law constant. So like y is equal to mx. The similar way you can also see here. So you should know that diffusivity or no solubility values are in certain cases the permeability values are given, and similarly you can also estimate the mass transfer coefficient in the gas film, the Kc1 and Kc2, because these are the typically we can exemplify that one component is transferring through the other component when it is non-transferring, like A is transferring through the non-transferring B. So where the Kc, that is the mass transfer coefficient, film mass transfer coefficient, will vary depending upon the concentrations. That's where the Kc1 and Kc2 values are different. And also the Kc1, Kc2 are different because of another reason that here the feed is maybe accompanied by the two components. One component is typically transferring through the membrane. Other component is not partially transferring through this one and reaching this side. So this side the concentrations are very low, and also sometimes you can use one more phase where it can create a certain concentration difference to enhance the mass transfer. So you can use one throw phase, so that it will take all the molecules which have diffused or which have been permeated through the membrane and reach to the other side will be carried away by that particular phase. So that phase is inert, but however in the inert phase you will find very dilute present of the component which is not having that much permeability through this one, and other component which is having access to the permeation, that component present will be very high, so that the concentrations are here compared to this side will be different. Therefore the Kc1 will be different with the Kc2. That's why we are using two different resistance and which are in parallel, so you can calculate finally the flux. So that is how the permeation flux can be estimated in a gas permeation operation. And you can see that certain permeability values are there, which I explained in the last class. But however, in a gas permeation, these are the four models which we have discussed to some extent in the last class. So the first model which we take is the complete mixing model, and the second one is the cross flow model. So where the flow is perpendicular to each other, the feed is moving in one direction, and permeate is moving an opposite in a upward direction. So one is horizontal and one other is vertical. So you can call it as a cross flow. And the third one is the counter current flow, and fourth one is the co-current flow. So you can use that, but we will discuss only this complete mixing flow in our syllabus. Only it is there, so we will not discuss these three. Okay. So when you take the complete mixing flow model, as I explained that the concentrations uh, across the membrane below will be constant. Similarly above, that means high pressure side and low pressure side, the concentrations will be same across the membrane over the length of the membrane. Therefore we will assume only Yp. Here we will assume only X0, which is also concentration of the reject which is coming out. Okay. Then we have, this is called, usually theta is called cut, means how much of feed is getting separated as the product, and which is having the desired composition of Yp. So that is the theta. So which is defined by the total volume obtained, volumetric flow rate obtained per volumetric flow rate of the feed. So then again, this is the equation which follows the same thing here. This is the partial pressure of the high pressure side. This is the partial pressure of the low pressure side. Then you have a permeability here, because we are only seeing that here there is no film. Film is completely disturbed due to the complete mixing. So we have only one resistance which is offered to the mass transfer is the membrane. So this is the membrane controlled operation, we can call it as, because that is also ideal in case of the membrane operations. So there is no film in the high pressure side, there is no film in the low pressure side. So Kc1 and Kc2 values are negligible here. Therefore we are only considering the flux through the membrane. So this is the flux through the membrane. So you can consider the permeability. Pa1 Pa bar is the permeability, by T is the thickness of the membrane, then this is the partial pressure difference. So this is the equation which you can write for the component A. Similarly, if you think that only two components are there, component A and component B, that is a binary mixture in the feed, then again for the component B you can write down this equation, where in place of Yp you can put 1 minus Yp. So because the concentration of A plus concentration of B in the product is equal to 1, therefore 1 minus Yp will give the concentration of the B component. Then you will be having a permeability of the B, and thickness is again same, and then this is the partial pressure of the B, In high pressure side, this is the partial pressure of A, partial pressure of the B in the low pressure side. So you will get the pressure difference, partial pressure difference. Then again, this will be the capacity of that, like similar to the mass transfer quotient. Then you can write two equations, equation 14 and 15. Then dividing 14 equation by 15, then you will get this equation. And here alpha star is defined as PA, that is the permeability of A divided by permeability of the B. So then finally you can have this equation, and this equation relates YP. YP is what? This is the product quality, the permeate composition. YP is the permeate composition to X0. X0 is what? The rigid composition. So it relates the YP versus X0, and the ideal separation factor is alpha star, is defined as the ratios of the permeability of A and permeability of B. So making an overall mass balance, then you can get overall mass balance of the component A. QF into XF is equal to uh, P into YP plus Q0 into X0. So that is the equation which you will get, and then you will get the one equation for X0 and another equation for YP. For example, here you have a relation between the YP and X0, and here also you can see YP and X0. Or if you take this one, X0 and YP, both are from the material balance equation only. So two equations, by knowing remaining thing, you can able to calculate your YP and X0. And finally, the membrane area can be calculated by using this equation. But however, you can see here, there are so many parameters which one has to see. That if you take the case one, because you can understand this complete mixing flow model, the solutions for the problems by taking two cases. In the case one, the feed quality and rigid quality, and then this is the system property, that is the ratios of the permeabilities, and PL by PS. This is the low pressure by high pressure. This is the operating uh, conditions, and this is system condition. This is operating conditions. These are the given system again, except, and this is the specification in the operation. So if you know XF, X0, alpha star, and PL by PH, and if you know that, then you need to calculate the product quality, then how much of quantity of the product, that is the cut which you will get out of the one volumetric flow rate of the feed, how much you will get as a product, and then the membrane area. These three are to be determined. Okay, and you have only one equation or hardly two equations. So solution is a complicated one. Therefore, you can convert this equation into in this form. This is a x square plus bx plus c. In this form, this is a quadratic equation. So where once you put in this form, this equation once you put in this form, then you can see what is A. A is 1 minus alpha star. The B is this much, pH by PL 1 minus X0 minus 1 plus alpha star pH PL X0 plus alpha star, and C is equal to minus alpha star pH PL X0. So when you know the X0, XF, alpha star, A, B, C can be calculated. Once you calculate A, B, C, then the solution for the quadratic equation is this one, that is minus B root of B square minus 4AC by 2A. So by knowing ABC, you can substitute here, and finally you can get the product composition of the component A. Then once you get this one, then use the other equation of this, like by knowing the YP, X0 can be calculated. Then by using this equation, you can calculate the membrane area which is required. So the case A will give you that by knowing the reject composition, how much of component A should be there in the reject. For example, any flue gases is coming out of the particular industry. So in the flue gas, you want to remove the sulfur or any hydrogen or any other organic pollutant, that is more volatile components, like you can say that the benzene, toluene, these components, if you have more, uh, that is threshold limits are exceeding, the concentrations are exceeding the threshold limits, then the vapors or the gaseous stream which is coming out is harmful. Then you have to remove that by using the, so x0 maybe can be fixed based on the threshold limit. Then you have xf, x0, alpha star, and pl by phc. So these are known. Then you can able to calculate the remaining. And if you having one x0 value, then you can also calculate how much of area is required, membrane area required. And if you see a real example, and you will be surprised that the AM value will be very large. So that much large surface area or membrane area cannot be created on a flat sheet. So you can use the configurations which we have discussed of anyone, then you can provide that much of area, you can get operation done. And in certain cases, you may know xf theta, because the product quantity this much has to be separated for a given volume. So theta cut is known, and then this is the system is known, and PL by PH operating conditions are known. So this is the specification. So xf alpha star is a system. It is depending upon the membrane which you have selected and its permeability through that membrane. Alpha star is fixed. Then the PL by PH is monitored by operator, that how much pressure in low, that is product side, and how much pressure on feed side you should maintain. So that is fixed. So you can call it as an operating condition. So once you know this, and this is the specification, then it may not be possible by solving that previous problem solution. Now the solution will be a different. Here you can just see that the yp x0 and the membrane area are to be determined. Therefore here you can again convert that into a different form, like a1 yp square b1 yp plus c1. Then here your yp is equal to, again equal to this. However, a1 in terms of the theta, you can again modify the equation. So a1 is this one, and b1 is this one, and c1 is this one. So where x0 is eliminated, and you have included the theta. So that's why the equation, the quadratic form of equation has been changed in this fashion. And again the a1 b1 c1 are calculated by using the known values of this. Then the finally you can calculate yp and go back to this one. From the yp x0 can be calculated. Then again you can substitute here and find out how much of area is required to get this much of theta. Here the cut is very important. So how much of a product quantity you are getting, that is very important. So you can get that one. So in one case x0 is fixed, in another case theta is fixed. Again you are finding out the how much area is required. But however, in a complete mixing flow model, you can analyze one simple thing. See, before means knowing the limited values. For example, how much the minimum possible of XOM means, you can fix XOM below the a particular value, but that may not be possible in certain cases. So this analysis says that what is the minimum possible of the rigid composition which you can obtain in case of the this gas separation operation. So if you take this one, see, if all of the feed is permeated, for example, see in here, if all of the feed is permeated here, then the YP value is equal to XF. Okay, your YP value is equal to XF. Okay, and it is said that if all the feed is permeated, then theta is equal to 1. Theta is equal to 1 means all the feed is permeated as a product, and the feed composition will become equal to the product composition. The feed composition and product composition will be equal, because like in a total condenser condition, what will happen once the vapors are coming out, if from the distillation column, its composition will be Y1. So if all the vapors are condensed, then in the condensate, that is in the reflux which you are sending back, so that will also have the composition of the vapors which are leaving the distillation column. That is the total condenser condition. So Y1 is equal to X0. Similarly here, if all the feed is permeating through the membrane, then XF will be equal to YP. For all values, what we know that theta should be less than 1, because this is the ideal one, and if this is not there, then theta should be always less than 1, so that certain permeate will come and certain reject also will come. So this is the real problem. Theta is less than 1. The permeate concentration is also greater than XF. So this will be there in a real case. So now if you rearrange the equation, this equation, which equation? This equation, so as to calculate the X0, so you will get this equation, the X0 in terms of the YP. Okay, so which means that X0 is a monotonic increasing function with YP. So whatever YP value is there, with that it will be more, isn't it? The YP is more, then this will be more. So what is the minimum possible YP? Minimum possible YP is XF, because if the all the feed is permeating through the membrane and gets as a product, then your XF is equal to YP. So otherwise YP is greater than XF, because YP will have more concentration than the your reject or your feed, and this is the minimum possible. So X0 is YP. When you make this one, you can see that if YP is increasing, keeping all other parameters constant, maybe system parameter or operating condition parameter, then X0 is a function of YP. When YP is at its minimum value of XF, because the minimum possible is YP is equal to XF, then you can substitute in place of YP the XF value, that is a feed composition, then the reject composition of its minimum is estimated. So this is the XOM means the minimum possible reject concentration in the operation can be calculated. How do you calculate that? XOM is equal to, by replacing the YP with XF, you can calculate. So now you know all the values. So you can calculate XOM. Now you can take a decision that by using this membrane and by using this operating condition, so this is the minimum possible reject concentration which we can obtain by using the particular system. If you are not satisfied with that, for example, say that the toluene concentration is to be reduced to a particular value, so the minimum possible value is more than the threshold value, then the membrane has to be changed or operating conditions are to be changed. So you have to take such decisions by calculating the XOM. So you can calculate the XOM by using this equation, and then you can see whether membrane is to be changed or the operating conditions are to be changed. Maybe you cannot means develop the pressure difference more than a particular value. It may break the membrane also. So there is a limitation with these values. In that case, you can take a decision that your membranes which has a more permeability to be considered, or if within the limitations you are getting the XOM value which is lesser than the threshold value which is allowable in the operation, then you can comfortably work with that particular membrane. So in that way you can take certain decisions during the operations. Hence a feed of XF concentration cannot be stripped lower than a value of XOM even with an infinitely large membrane area for a complete mixed system. To strip beyond this limiting value, a cascading type system for a single unit of plug flow should be used. So in that case, you can also use a cascading system, means in unit 1, unit 2. So unit 1, whatever reject is coming, that will go to the unit 2. So whatever is coming, that will go to the unit 3. Like that you can strip, because the feed reject which is coming from the unit 1 will become a feed to the second unit. So in that way this value is go on reducing, and finally you can get the required separation by using a cascading system. So that you usually see in a equivalent governed operations where the number of stages are estimated. Similarly here also you can do that. So this complete mixing model very simply you can make us to analyze the given system whether it is possible to um, proceed with that particular system for the separation, or can we use a single unit or a multiple cascading unit, or within the limits the membrane, if you change the different membranes, maybe any membrane will give us the alpha star value which is greater, and that may give the XOM is a lesser value. So that decisions can be taken by using this particular equation. Okay, now let us do some problems in both the case, like case 1 and case 2. So the first problem, all of you can note down that a membrane is used to separate a gaseous mixture A and B whose feed rate is, so this is the volumetric feed. See, particularly in gas case, the conditions are to be maintained. At which conditions? STP, standard temperature and pressure. So this is the gas flow rate, centimeter cube per second, and the feed composition of A is 0.5. So this is the mole fraction. The desired composition of the reject is this much. So this is the desired in the operation. The membrane thickness is this much, 3 into 10 power minus 3 centimeters. And then the feed side pressure, that is a high pressure, is 80 centimeters of mercury, and low pressure permeate side pressure is 20 centimeter Hg. Then the permeabilities are having the units centimeter cube at these conditions per a centimeter. So through a membrane area of the centimeter square, when you are having this much of pressure difference per a unit, so this much is possible to pass through the membrane. So that is the units for the permeability. Permeability units, you should remember the centimeter cube STP per centimeter divided by say centimeter square and centimeter Hg and S. You can use the pressure units depending upon the permeability. If the permeability is giving centimeter Hg, then your pressure values are to be centimeter Hg. If they are having mmHg, then you convert them into the mmHg depending upon the permeability value. Or sometimes you can also have pascals and all those things. So accordingly you can take the pressure values. And then this is the permeability of the second component, uh, assuming the complete mixing model, calculate permeate concentration, that is YP, fraction permeated, so that is a theta, how much um, is permeating through the membrane, and the membrane area. So as I explained in the case 1, like xf is known, x0 is the desired value is given, and alpha star you can calculate from these two values. Then the low pressure and high pressures are given, the pressure driven operation. So you can see what is the pressure imposed across the membrane is given, and then you have to calculate this thing. Okay, so what are the cut and YP, product composition and membrane area are to be determined. Then you can use this will be case 1, then you can use this equation, quadratic form of this equation, where A is equal to this much, B is equal to this much, and C is equal to this much. So again alpha star can be calculated, so it will be 10, and then A will become -9, and B will be calculated by using this equation. So the pH, PL, and also x0 is known, and then finally the B value will be 22. Then the C value is calculated by using this equation, where all the values are known, then it will be -10. Then substitute here and calculate the YP. So YP is coming as 0.604. So that means the XF value is 0.5 here. XF value is 0.5, but where is YP is coming as 0.6. Okay, then you can calculate the X0. So by substituting this, X0 is 0.25. So it is satisfying. It is satisfying, no? The X0 is 0.5 you have taken here. So 0.25. So it is satisfied. You can calculate that. Now you can estimate the theta by using any one of that equation. Okay. So here theta is 0.7. That means 70% of the feed is obtained as a product. Only 30% reject is there. Then the membrane area can be calculated by using all these things, because every values are known. So finally you are getting the membrane area which is required is 2.7 into 10 power 8 centimeter square. Very large area. 10 power 8 centimeter square means very high area is required. For example, if you remove 10, maybe 10 power 2.7 into 10 power 4 meter square. Okay, very huge area is required for the getting separation of very less, maybe 0.5 to 0.6, 0.5 to 0.6. Okay, so you can now go for a different type of configurations which will provide this much of area in a small space. So that is also very important. You cannot utilize all the area which is there in the chemical process plant for the membrane unit. So you have to reduce a very compact membrane unit has to be used. So that is a very you can select the configuration, spiral wound, or plate and frame, anyone which is giving you this much area, and also making a good contact and withstanding the pressures which you impose over that. Okay, and similarly this is another problem. Please, all of you, please note down this problem. Also, it is desired to find the membrane area required to separate air using a membrane 3 into 10 power minus 3 centimeter thick with oxygen permeability. The PA star is this much, and alpha star is 10. So that means PB permeability of the other component you can calculate. Oxygen means nitrogen can be there as a mixture in the air. So the membrane which is used is separating the oxygen and nitrogen. So per permeability ratio of oxygen to nitrogen is 10. Feed rate is this much. and fraction cut theta is 0.2, means 20% of the air which is entering into the membrane cell is to be obtained as a product, and which should have certain concentration, because that we will calculate. Then the pH high pressure side is this is the value, low pressure side this is the value. Assume complete mixing model, calculate the permeate composition, that is YP, and reject composition, that is X0, and membrane area. So membrane area you should calculate. So this is a case 2 where we were not knowing either XF, either X0 or YP. So this is హలో గుడ్ మార్నింగ్. నేను ఒక క్లాస్లో ఉన్నాండి, ఆన్లైన్లో మాట్లాడతాను. Then A1 can be calculated as I have given already equations. So where no X0 or YP are present, only cut is there, and the pressure differences are there, and permeability differences are there. Then A1 is coming, and B1 is coming as 5.41, again using this equation. Then the C1 is this one, then you can substitute here and get YP value. Okay, so once you get the YP value, substitute in the mass balance of the component which is having more permeability, so you will get the rigid composition 0.135. okay, so YP is 0.509, and this is this one, and finally you can get the area 1.21 into 10 power 9 centimeter square. So this is the area which is required for that one. So this is how you can solve very simple problems in case of the gas permeation, maybe hydrogen permeation or oxygen permeation or any other organic vapors permeation. You can solve the number of problems which are available in the books or in the literature. Okay, so that is how you can able to solve the problems which are related to the gas permeation. Now very important operation is the reverse osmosis. So all of you know the principle of reverse osmosis. Here you have we have the salinated water. Hello, hello, who is that? How many are present?